Yeah. So, and the reason of using this, it actually emulates the down-converted signals coming from the translation board, receiver board, and it mimics the signals as the phase signals coming from that, and sends it to the ADC board and then to the FPGA. So the reason using the system provides an easier way to test the system rather than dealing with all the issues in the entire system. So a big picture for the overall system. So we have the LabVIEW interface here. It configures the 4 signal generators. The signal generators are dual channel, so each of them generate 2 signals. And then the LabVIEW interface basically sends out enough information for the signal generators to mimic the 8 signals mimic the signal coming to the 8 antenna array. And as they like ping on the array and then go all the way to the translation board and then down converted and then sent to the DAC card. So that's what the LabVIEW and the signal generators are for. And then this one sends the signals to the ADC board through SMA connections. And then the ADC board, of course, is responsible for sampling these signals. It operates currently at 2 rates. They're configurable in real time. Operates at 12.5 megasamples per second, as well as 25 megasamples per second. It's configurable through bit switches in the FPGA. You can pick whichever sampling speed. Currently, we use it only at 25 since we're more interested in higher sampling speed to hit the WiMAX radio bandwidth. And then, so the FPGA configures the ADC board and configures the speed of sampling or rate of sampling. Also sets some parameters in the ADC board, such as how we want to receive the data, in what format, two's complement or offset binary, as well as when the ADC board sends the information to the FPGA through the differential lines, LVDS differential lines, it sends them serially. So the FPGA would receive for each channel, it's sent serially a stream of bits. So the FPGA packages those bits into bytes that represent each sample. But all 8 channels are digitized simultaneously. So the serial part is only for streaming the bits. And then, and then we use the chip scope logic analyzer, which is an analyzer that can be integrated inside the FPGA in order to monitor the internal signals and verify the functionality of the internal components. Since traditional ways of testing systems in general using oscilloscopes and logic analyzers, they won't apply to the FPGA because all the systems embed inside the FPGA. So we need some sort of system that can be integrated inside and send all this information to the computer in order to be analyzed. So now we're going to talk about the Bartlett DOA estimation. So Bartlett is a Fourier spectrum analysis method. The goal is to find set weights that maximize the received signal power. And then the estimated DOA is represented by peaks in the power spectrum. It's a simple algorithm. We started with this one due to its simplicity to implement in our system and to verify the functionality of the overall system. So system was both implemented in hardware and software. It consists of the ADC driver, which, as mentioned, is part of the FPGA. It configures the ADC board, and then receives the samples. Then the FFT module, which performs fast Fourier transform for the sample data, and then we do frequency detection and perform the DOA estimation algorithm. That's flowchart show the functionality of the system. So the first implementation was custom HDL implementation, which usually referred to as hardware implementation too. So the ADC driver here is connected to the ADC board, receives the signals. Also, it configures the ADC board through a SPI line or lines. So, and then once the data starts streaming in, this ADC driver packages them into bytes and store them into a block, 8 block RAMs, one for each channel, and it's 1024 points by 8 bits wide. And then once the sampling of the 1024 points that we need to perform the DOA is over, the ADC driver sends a signal to the block FFT in order to start analyzing and performing the fast Fourier transform. Once that is done, the fast Fourier transform, the results are stored in a 1024 by 18 bits wide memory blocks. The reason it's 18 because the results of the FFT contain real and imaginary data, and then the reason each is like 9 bits is because this data is unsigned. So we do a sign extension and then perform the FFT. The output is 9 bits per either real or imaginary. Once the FFT is over, a signal triggers the frequency detection, which goes through only the first channel and detects the maximum or the frequency of the incoming signal. And then once that is done, it's a quick process. It triggers the DOA Bartlett algorithm to compute and estimate the direction of arrival. Once that one is done, they both send the frequency information and the direction of arrival to the LCD controller to view it on the LCD on the FPGA. So talking more about the FFT, as mentioned, it's 9-bit, 1024 points, 8 parallel channels. It performs all the channels of all the 8 channels all at once simultaneously. And we use fixed point for a lot of considerations, mainly resources, because the FPGA won't be able to fit 8 channels floating point FFT. Also, I use the Radix 4 implementation. It's basically the Radix 2, but they put 2 Radix 2s to run in the same stage. So it gives us twice as fast performance, and it only completes the transform in 5 stages for a 1024 points, rather than 10 stages in the Radix 2. So basically, this means it's faster. And then detecting the frequency, calculate the magnitude of each FFT bin in memory, and then find the maximum, which represents the location of that represents the frequency. And in Bartlett algorithm, we stored the weights in block ROM. This way, we don't have to calculate in real time. And since we divided the space into 8 sectors, basically the Bartlett algorithm only detects the signal from like 8 directions. So what that means is that if a signal coming from 10 degrees, let's say, it will say that it's coming from the first sector, which is 0 degrees. So it's not high resolution, but it performs quickly. And it's only for to verify the functionality of the system. So we use the matrix multiplication using one multiplier and cycle data through that. And the maximum power, which tells us the estimated direction of arrival, is found by comparison. So here's a picture again for the hardware implementation. The ADC driver was written in a custom VHDL. We generated the sample RAM, the FFT RAM using Xilinx core generator to save development time. And since it's provided and optimized, the frequency detection part of DOA were designed in custom hardware. So next, we're going to look at the microprocessor-based implementation. We used Xilinx Microblade soft processor, which is a 32-bit RISC processor. So the ADC driver is still in custom hardware. It's going to stay like that since it's optimized and it's running just like something.